All right, well, welcome everybody. Thanks for the great turnout today. We are pleased to welcome Professor Huaizu Jiang from Northeastern University. He's an assistant professor there. He started in 2018, 19?
21.
Oh, really? Wow. Well, then we'll see lots of impressive work in a short amount of time since he started. Professor Jiang studied under Eric Leonard Miller at UMass Amherst. So he's a Northeast staple at this point, with multiple internships at NVIDIA and some time spent working with them on the West Coast as well. Today, he's going to be talking about a whole set of different techniques that all concern, right? that all concern what it takes to be able to make realistic working scenes from a computer vision perspective, not necessarily from a computer graphics perspective, and then what it takes to populate them with human beings that can interact with objects and the 3D scene as well. So we're very much looking forward to your talk, and thank you very much today.
Thank you, James, for the kind introduction, and thank you for having me. I'm very excited to be here today talking about our lab's recent effort, and the title is Generating and Populating 3D Indoor Scenes. Okay, so recreating the physical world around us in the digital form has always been a grand goal in computer vision. So, for example, you can take your cell phone wandering around somewhere, for example, in your apartment, take video, and later you can reconstruct the scene, right? So, what do I mean by reconstruct? So, first of all, we like to recover like the geometry of the scene, right? So, for example, the shape of the table, the shape of chairs, and other stuff. And also semantics, right? What are in the scene, right? Like chairs versus couch, bed versus other stuff. And also materials, right? Now, what's the floor? What's the material of the floor? Is it wood or something else? And also lighting condition, right? So, the recreated scene or digital model, or modern term like digital twin of the physical scene would look differently if the input were from different lighting conditions, for example, daytime versus nighttime. And also physics, right? So, for example, I have a water bottle here. If I happen to, put it down, something may happen, right? So all of these factors makes this kind of, reconstruction problem or task notoriously difficult. So we have made exciting progress along so many years, but still a lot of things, to solve. And if we look back, there are some like interesting slide paradigm shift, right? So before people used to, use those old geometry. I shouldn't have said old, but like classical, geometry principles are still useful nowadays, right? So for example, like this famous system called map, right? So it takes a huge amount of ordered or even unordered images and recover the poses of cameras and also do a sparse reconstruction of the scene, and later you can do something like multi-modal stereo to densify it, right? And about like 4 years ago, this exciting technique was introduced, like neural radiance view, and more recently 3D Gaussian splat effect. And now with more or probably denser input, we can really have photorealistic rendering of the scene. So this is about reconstruction. By reconstruction, I mean, we have a lot of input or a lot of visual information in the input to constrain what the output should look like, right? And so here our lab also did some effort, something in this direction. So for example, with this video I just showed you, in the right, I'm showing the reconstructed planar surfaces, for example, like ground floor, table surfaces, surfaces of the couch, right? So, planar surface reconstruction is a specific type of reconstruction where we were mostly interested in, recovering those geometric primitives, the planar surface, right? At the same time, there is another, very interesting line of research. It's about like generation, right? So by reconstruction versus generation, I mean, in the input, there's little, almost no clues about what the output should look like, right? I mean, like visual clues, right? For example, in this send word 0, 1, 2, 3, the input is just a single image, right? So we do not have information about other parts of the scene, and the goal is to synthesize an image of the scene at a totally different view angle. For example, probably from complete opposite of the object, right? So, really it involves a lot of hallucination to guess, what the scene looks like. And this also very famous work, diffusion, right? So it accepts a texture from a texture description, for example, for this one, probably like a raccoon wearing astronaut suit, holding a helmet, something like that, right? So the model, can hallucinate what it should look like and produce some like 3D, output. In our lab also work in this direction. This is our recent archive, where we started from a single image and we convert that image into a 4D content or multi-view dynamic scene generation. Right? And with that, today in the first part of the talk, I'd like to talk about something in this line. We start from some like a floor plan, right? So this floor plan has little information about the 3D scene. It does have some information, but not too much, right? And we design a model to convert it into a 3D scene in some explicit form, more specifically in mesh, so we can later have more like natural interactions with the scene. And you may wonder, why we should care about reconstruction, 3D reconstruction or generation, right? Because we can do a lot of cool stuff with that. For example, with the reconstructed planar surfaces shown in the left, we can add some AR effects, like just drop a lot of cubes in the scene. And because we know, oh, there is a couch surface over here, so when those cubes drop off, they should not penetrate, right? They should stay over there, no matter from which view you look at the scene or you render the scene. So that's very important application of this language research. And another very important task or downstream application is about like populating the scene, right? What do I mean by that? It's really about asking what would or could a virtual human do in the digital form, in the digital world. Like what we humans have done in the physical world, we've invented a lot of tools. We build those buildings, houses to make our life easier. And here, if we just had an empty digital world, it's meaningless for us, right? So we like to populate the scene to have some virtual humans there who can have meaningful interactions with the surroundings, with other peers, or probably even have interactions with our physical community. Right? So with that, in the second part of this talk, I'll be talking about how to generate human motion, right? So how a virtual human can move around and have some meaningful interaction, and also have meaningful interactions with dynamic objects, right? So I'll mostly focus on the first and the third, and briefly talk about the second one, just for the sake of time. And if I do not make anything clear, feel free to stop me. Okay. So let's start from the before that, a lot of application for this language research, for example, therapy, right? Imagine what if we could create a cozy like room or apartment, and you can talk to a virtual human without worrying about privacy and other stuff. And also gaming entertainment, right? To have more authentic experience, and also like sports. What if we can hire Messi to teach you how to play soccer, right? And also e-commerce. Say I am a manufacturer and I have invented some cool product I like to showcase to general people like audience how we can use this cool product. So that's kind of the research. Of course, we can help our robotics friends, roughly like having a simulator and then transfer that everything we did, everything we do in the digital world to the physical. So this is the plan. Let's start from the first one. Again, feel free to stop me if anything is unclear. Okay. So how can we generate a 3D scene, right? When we talk about generating and generative models naturally come into the picture, right? So nowadays, the mass generative models are mostly all based on diffusion model, except for the latest release of movie gen that uses slightly different technique. Anyway, So I'd like to start with a brief review how diffusion models work for image generation. And then we can see how we can, adapt that for 3D scene generation and also for human motion generation. So for a diffusion model, it works, it consists of two processes, right? So we start from some clean signal. By that, I mean, for example, like clean image. And then in the forward process, we gradually add a lot of noises, typically Gaussian noises, to this, clean input. So, in between of this forward process, we may have something like this, right? So it has noises in the input. And after, add this process of adding noises, after T steps, we'll end up having a pure noisy image, a Gaussian noise image, right? So this is the forward process. And then in the denoising process, our goal is to gradually move or remove the added noises until we have a clean image. So that's the process of image generation, right? The problem is during the forward process, we know exactly how the noises are added or how the noises are blended together with the input. But in the denoising process, because two signals have been, blended together, it's really, there's no closed form or analytic form to tell us, what the residue or what the, added noises are like at any intermediate process, right? So typically, so basically this Q function is really hard to obtain. So typically we use a parametric model, for example, MathWorks to approximate this process, right? So we have some like parameters of data. And in some cases, we may have some actual input, like in addition to this Gaussian noise, we may have some like textual prompt or natural language description about what type of image we like to generate. For example, here, a dog is sitting on the bench, right? So, so the model accepts another input, a textual prompt, right? And this parametric model for image generation, it can be unit, transformer, or something else, right? So this is generally how it works, right? So we can, of course, extend this to 3D scene generation as well. For example, in the CVTR paper, they started from some voxels, right? So if you're not familiar with voxels, you can roughly think of them as cubes. We can partition a 3D space into a set of cubes, right? They are in analogy to pixels in the 2D image, right? So, and then we start from like noisy voxels and gradually denoise or make them more like, realistic until at some point we have this like kind of good looking, voxels partitioning the 3D space, right? And on top of that, so basically here, only geometry. We do not know what the apartment, the scene look like. We have no color information yet, right? So in this paper, they added some textures or color information as a post-processing step, right? So to look like this. So the problem of this paradigm or this approach is that, generally high quality 3D data is harder to acquire than 2D images, right? We can easily crawl a lot of images from the web, but not so for 3D images, right? So, and even for some 3D information like voxels, they cannot be directly mirrored, right? They can, they're mostly like intermediate, output of a computing process, right? So this a limit of native 3D generation model, right? Alternatively, people have investigated, using 2D generative model to help 3D generation, right? So for example, in the left, so they employed a 2D generative model to generate images along different locations of the scene, right? The problem is, however, is that you can see in generated scene is not in a consistent form. Like the geometry is kind of distorted, for example, like this wall. Right? And other people also, investigated like single room generation starting from a 3D proxy room. By proxy, I mean a user has to specify, in the first place, oh, there is a bed over here, and the bed is roughly within the 3D boundary. Right? But the problem is, they only investigate the room scale, just a single room generation, right? That's not enough. Typically, or ideally, we should have generation of the whole house or apartment. And also, this 3D proxy room in the input is somewhat, not that natural. So, it takes a little bit more effort for the user to specify a 3D bounding box over there, right? And here's another effort, right? So they started from this 2D layout, right? It's more natural to start with than this 3D proxy room. But they only focused on single room generation, and their final product is a rendering model. So there's no explicit 3D model like Mesh, right? So having access to an explicit 3D model is useful for a lot of downstream application. For example, the cubes drawing effect I showed you earlier, that requires us to know where the couch is exactly in 3D, right? So this is something about some existing work. And what we're doing, bearing all of this constraint in mind, what we're doing is to start from this 2D floor plan, right, to generate a 3D scene, right? So the 3D scene, we know exactly where those stuff are in 3D, and so we can have access or some editing directly over the 3D model. So how does it work? So first of all, house scale generation with explicit mesh output. So how can we approach this, right? Like I said, native 3D generation is not a good idea. So we also resort to 2D generative models, right? So we started with partitioning this floor plan, into or converting it into a graph, right? So here each node represents a place, in a virtual scene where we can visit or have access to generate a set of observations about what this scene looks like, right? So for example, here we can generate some images at this red nodes, right? And with the help of this multi-view observation of the scene, if we can generate the images or observation at different locations, right? So as if we were taking a video inside this house, later we can use this multi-view observations to reconstruct the 3D scene. Right? So this is the overview. So this is the illustration process of how it works, right? So each time we visit some nodes, like those red nodes, and we generate some images at those red nodes, right? So, and those blue nodes are its neighboring nodes, which I'll explain what that means. So in the right, so each time we generate some multi-view observation, more specifically RGBD images, right? So we generate both color and depth information at different locations. So I'm showing here the generated images in the point cloud format, right? So you can see the point cloud incrementally grows up until we exhaust visiting all different locations in the scene, right? So we gather a lot of observations in the scene so we can reconstruct the scene and finish the generation. So this is the pipeline of the approach. Anything clear?
How do you start with the mesh?
Yeah, that's a good point. So we do not have mesh to
Oh, sorry, the
graph. Yes.
Yeah.
So we typically start from this graph is really like a tree. So we start from some leaf nodes, which can be here or here. We just randomly choose a place to start with. So here, in this case, it happened.
Like, are you given a schematic of the apartment?
By
The floor plan.
yeah, so yes, this floor plan is the input. So we know roughly, or the structure of the apartment or the scene. Okay. Okay. Let me move on. So at each location, let's say now we are at these two red nodes. So remember, this is an incremental process, right? When we reach at these two red nodes, we know we have generated images at this, at this neighboring node or those blue nodes, right? So we need to deal with some consistent issue, right? So what should those images in this blue nodes look like, right? So here we have some actual information to help us, right? First of all, we know we have generated images in these blue locations, right? Like I said, we generate RGBD image, right? So, this color image and also depth information. So here, blue means that particular, stuff is closer to camera, and the green or yellow stuff are far away. So this is, one piece of information that can be helpful for us to, to guess or to generate images in this red node. So what we do is to use a 2D diffusion model, right? So we use a stable image diffusion model, and it takes this, we call it reference images, because they are at the neighboring, they are from the neighboring nodes of this two red ones. They tell us, what are already in the city because they have some overlap in the view, right? At the same time, we also have some useful information from the layout, because the layout or the floor plan tells us, oh, probably there should be a table over here, or there should be a bed over there, right? So we basically take these two type of information reference images from the neighboring nodes and also layout of this just local view, right? All the information in this layout, because they're far away from these two red nodes, which then use that. With this two, technically speaking, we use them as conditioning signals for this 2D diffusion model, and then we generate this target RGBD images. Right, so this is what happens at each batch or step. Yes.
How exactly do you encode the layout?
So what's that?
How do you encode the layout?
Yeah, that's a good point. So for the layout, because the layout is because we're talking about generating images, right? The generation of the image is dependent on the camera pose at each location. So in a high level sense, we transform the information of this local 2D layout into some camera view dependent latent or features. And then because these 2D diffusion models work on the feature level in latent space, right? So in a high level sense, we transform the local 2D layout into some camera view dependent features, and which are then fed into this 2D diffusion model.
Yeah, how many images do you render for a red point?
Yeah. So here, how many images to render at this target location is dependent on within a certain physical space, like how many views are over there. So it's possible that here we may render images for 3 nodes, here only 2, or in some cases probably just 1. So that's a variable number. And also for the for the reference images, right, depending on how many neighboring nodes we can cover within certain range of the camera views, right? So this number is also variable. Yes.
I'm wondering if it's possible to generate the depth maps for reflective materials.
Yeah, that's a very good point. So here we didn't, we somewhat disentangle the output or the generation of appearance and geometry, right? But for the appearance itself, it's an effect of lighting condition, materials, and other stuff, right? So for that, we haven't touched yet. We simply assume there's some certain lighting condition dependent, or the model learns that from the training data. And here we do not explicitly do that. So we just take everything into the RGB. So, if in the training data, there are a lot of this kind of reflection, the model probably can do that, but it's not the model we control. Okay, so I'll move on. So here I'm showing the generated RGB images in the point cloud form, right? So you can easily see the correspondences within these 2 blue circles, right? They're all about this cultures or schools, or within this green circle, they both cover about this wall area, right? So in other words, the already generated images in this blue region are helpful, or they constrain the generation of these red images. But in other words, because we resort to the neighboring information to guide the generation of new batches, right? So naturally, the consistency of the global scene generation is ensured. Right? 2 things. One is the floor plan, guidance about the floor plan. Second is about borrowing information from the neighboring.
Are there any inconsistencies between the neighboring scenes and the overlapping sections between the generated and the neighboring scenes?
Yeah, so theoretically that shouldn't happen, but in practice, yes, we did observe some inconsistency, mainly because of the the depth estimation. The RGB images, surprisingly, they look okay, they look good. But if you actually project that back into 3D, inconsistency happens. So we have some like post process filtering to remove that one, and also the reconstruction approach also can tolerate that type of noise.
Can you talk a bit more about how you synthesize the RGBD image? Is there like a diffusion model for that?
Yes, so we in the input we denoise the latent or the feature representations of both RGB and depth images. So we convert both RGB and depth images into a latent space, and we denoise the latent their latent vectors. And then in the end, after the denoising process is done, we have two set of representation, one for RGB images, the other for depth images, and we separately decode them.
Also, you train a diffusion model yourself?
Yes, we
Oh.
we fine tune a already pre-trained model like stable diffusion. So here, the idea is, or the motivation is really the 2D diffusion models have seen a lot of images, billions of images, right? So it should have a good like knowledge or prior about what visual scene should look like. We start from that and fine tune the model on the data set.
Can you reiterate one more time about how you ensure consistency? So is it like, do you just pass the neighboring data to the network and somehow through the latent representation? It can
Yeah,
figure it out?
so we have some way to encode the input, like neighboring RGB images, RGB and actually depth images, and also the layout. So we convert all of this into some latent space and build that into a neural network to guide the neural network to denoise the latent representations of the target images.
So simply because you fine tune it on data that is not inconsistent, the model learns to keep the consistency when you run
Well, so
inference?
here, so for the diffusion model that we chose to start with, this model is designed to generate a single image at a time, right? So here, that's why we need to fine tune the model to adapt the model to accept multiple images at input and also generate multiple images at the same time. Of course, the model will also need also accepts the layout as actual input. Right? So regarding the consistency, intuitively we have the guidance from the layout, because this layout tells us, in a global manner, oh, there's something here in the scene, there is another thing in the scene, right? So, and also we have the help from the neighboring locations to help us or to constrain the generation of some local region. Okay, so I'll move on. And with the generated images here at this location, and we can merge it into this scene, and then keep doing this in an incremental manner. And when we finish visiting all the nodes here, you can roughly think of those nodes as as places where we can put a camera there, right? So they are at different empty space in the scene. So this is the final generated mesh, point cloud. And with that, with some TSDF fusion or some classical approaches, we can convert the RGB and depth images into this 3D mesh.
How did you choose which node to visit in the graph?
Yeah, so this node, after the construction of the graph, so we can randomly start from somewhere. Typically, we start from some leaf nodes, and then just do some breadth first or depth first search to finish with the entire graph.
Is there a different strategy affecting the final result?
That's a good point. We haven't rigorously tested that, but the problem is for the diffusion models, we recall each time we start from Gaussian noise, right? So depending on the starting point of noises, we can ensure the layout, the consistent the layout, but the color may not be always consistent. In other words, we'll end up having two houses that have exactly the same layout or the exact appearance, like color may be different. So that's one thing. In some cases, it's useful if you like to have diverse output, but in some cases, it's problematic if you like to have like, controllable generation. I just want to, change this part of this. For example, I want to change the color of the ground floor without changing everything else. So let me show you more results here. So this is another output, right? So slightly or different layout. So we can see this is the couch, two chairs, another one here. So, faithfulness to the layout is reasonably good. And here's another generation output. Oops. Again, something in the living room. So we also did a comparison with existing approaches, but here it's hard to do apple-to-apple comparison because different models accept different input, right? So here, our model accepted floor plan, but the other model accepts some texture problem. So what we did was to describe this floor plan and imagine what the scene should look like and write down some like textual descriptions. And we feed that into another system to generate the 3D scene. So, because this model has no guidance of this global layout, right? So it has basically too much flexibility when generating those images. As a result, the geometry is not consistent.
Can I ask you a quick question about the box layout in the floor plan? Does the floor plan encode the types of what objects?
Yeah, so I should have mentioned it's a vectorized only. It's not a plain image. So what do I mean by that means we know that there is a value here. Yeah. But
I'm just wondering about the pros and cons of this approach versus something that's non-learning based that basically just uses geometric heuristics to extrude all the walls and then retrieves instances of these objects from like a big 3D model database.
Yeah, that's right. So
Yeah.
I'll briefly talk about here.
Okay, great.
Yeah, so limitations and the future work, of course, have to admit those those general images, the quality is not that photorealistic, partially because we fine-tune the model on a synthetic data set. So with to some extent destroy the capability of the original diffusion model, which has been trained using billions of images, right? So that's one thing. And second, we separated the generation, the hallucination, and the final reconstruction of the scene into two separate processes, right? But you can imagine if we do it jointly, there will be better opportunities to allow each sub-module to compensate for the errors of the other. That's one thing. Second is it's related to one question raised over there, right? So we here slightly disentangle the geometry, depth, and appearance. But ideally, we like to have disentangled generation of everything: geometry, text, texture, material, and lighting condition. Right? Why this could be useful? Because a lot of artists or engineers have produced a lot of cool 3D assets already, right? So it makes no sense to completely discard them. But if we like to say retrieve or put a couch, get a couch from a gallery and put that into the scene, we would have to know, for the already generated environment, what does the scene look like? What's the lighting condition? Otherwise, it will be fake. So I think this retrieval, back to your question specifically, retrieval augmented generation and this pure hallucination approach are fundamental. And one more thing, right? It's very ambitious goal, but for our robotics friend, how about like having a pure generative simulator? So we'll have more diverse environment to train the embodied agents. Right? Okay. So let me switch to the gear to briefly talk about our effort on human motion generation. I'll start from this controllable motion generation group. I'll briefly talk about this. So this is what we have seen about the paradigm of generating images, right? Starting from some Gaussian noises, and this Gaussian noise can correspond to some like real image or like some latent feature representation of the image. So we can also adapt this to human motion generation, right? So similarly, we start from like Gaussian noise, and we use a parametric model, typically the transformer, to generate this, human motion sequence, right? So depending on the representations of the human body. So here in this talk, I'll be using the human joints, right? So we can represent each human at a particular time step with a set of joints, for example, head, shoulders, pelvis, and so forth. And we generate the entire sequence at the same time. For example, if at each time step we have 5 joints to represent a human body, and we like to generate 10 images. So the output or the dimension of this Gaussian noise is then 55 by 10. Right? So we generate the joints positions of all the humans in this sequence at the same time. So this is how it works. Right? And turns out this works well for reasonably well for human motion generation. Like here, the textual prompt is a person kicks. Right? So here, prompt is runs, simply a category label. We can see the results are reasonably good, but the problem is they may not be enough. We use this model to generate human motion in practice. Why? Because in some cases, for example, I am a game designer. I like to control a character to move in some certain trajectories, right? Of course, you can say I can describe those trajectories in natural language, but the problem is those description may not be always accurate. So here, we study the controllable generation where we allow the model to accept another input, right? The spatial trajectory specifying the positions of a human's joint. For example, in this case, pelvis in 3D. So we ask the model to generate motion where the human's pelvis follows this trajectory. This trajectory can also, like this is the S shape. Or this actual input or spatial constraint can be sparse, right? Here it's dense. We specify the location of the pelvis at each time step in output. Here sparse, by that I mean we can only specify the output at a particular location. So for example, here we like the human to move toward the chair and then sit down and then walks back, right? We specify the location of the pelvis here to be around the surface of the chair, right? So this is what the output look like. Right, so the actual input, the trajectory can be dense, can be sparse, and it can also be about multiple joints at the same time. So how it works, right? So this is the diagram about how a diffusion model can be used to generate human motion. And if you're familiar with the terms of diffusion models, right, there's a technique called classifier guidance. Roughly speaking, the idea is we can define a score function. This score function needs to be differentiable. It tells us, how good or how bad the model's output satisfies something. So for example, in this case, the score function accepts the trajectory, right, the S shape, or just a single point in 3D, and also the output of the models, output of the model. And based on this, it tells us how coherent this model's output is with respect to the actual specification of the user. And if we can do this, so roughly you can think of this as a loss function for your neural network, right? So it's objective function, and if we minimize it, or if the initial, the satisfaction is not that good, the score or the loss value will be large, right? And then we can do gradient descent, right? Because this function is differentiable, the generation of human joints is also parametric, and then another parametric model, right? So we can do gradient descent to update the human joints, to make the positions of those control, for example, pelvis, the position to be closer to the input trajectory. So this is how it works in a high level sense. And we can do this gradient descent multiple times, right? We do not have to do it just once. We can do it multiple times, and then we can better control the generation of the fusion. So how does the score function look like in this particular case, right? So say the black joints are from models output at a particular location, and this blue one is from user input, right? So this is the green trajectory I showed you earlier, right? So we can calculate the distance between the model's output and the user input, right? This distance tells us how good the model's output is with respect to the input, right? And this distance function apparently is differentiable, so we can do this gradient descent like stuff to make it closer. Of course, we can do it multiple times, right? So this is in high level sense how it works. And for the entire model, we have another design to make the generation motion more authentic. But I'll just skip that. So here in the left, we can show without this spatial control, so the model's output control completely ignores this trajectory as shape trajectory, right? It simply follows the textual prompt. And in the middle is output from a previous approach. We can see at the beginning, the generation is faithful to the trajectory, but in the end, it drifts away. And our approach performs a reasonably good generation, and the output follows the specified trajectory. And for that score function or distance function, we can do it, we can define it for multiple joints, right? That really gives us the flexibility of controlling multiple joints at the same time. For example, here, for some reason, this scene has a low ceiling, right? So the person has to bend over at the same time. We ask the human to put their, right arm to be close to the stuff. So generate something like this. Or in the right, let's say, the control points are scores. For example, pretend there are two cups over there. We like the human to move forward to grab them up. So this is how this model works, where we're doing controllable generation. Now you may wonder, what if we give the model some extreme controlling points like this spiral line in 3D? So we can see the model can still produce some reasonably good results. It's just the case that the human may float in the air, right? It's like it climbing up and down and completely ignores the rest context, right? So this actually is the limitation of this approach. But first of all, let me show you this interesting output, right? The prompt is a person walks forward and then picks up a cup. You see any problem? Let me show it again. Right, and the beginning of the generation, the motion is natural. The person naturally moves forward, right? But when the arms is close to the cup, the motion suddenly slows down, right? This is because of the formulation of the diffusion model. Recall I was talking about generating multiple frames at the same time. That means we need to specify how many frames to generate in advance. Now you can imagine for some motion, probably 10 frames is enough, but for some motion, 10 frames probably is too much or too few. So that's one issue of diffusion models. And the second, like I mentioned, right? So we have from a designer or user input perspective, we have to specify these constraints in advance. But imagine, this person, I don't know, for some reason decides to lift the chair up, right? Then the trajectory of the chair move variables when the interaction happens, right? So we cannot easily specify that trajectory in advance. So in the last part of this talk, I will be talking about how can we generate humans to interact with dynamic objects, right? And turns out this is a very challenging task, because imagine if we like to, generate everything from this textual prompt, we have to generate the human motion and also appearance or the, model of the 3D object, and also its motion, right? This is too difficult, so we decided to make it slightly more doable. So we assume the 3D model of the object is given to us, so we do not have to worry about the generation of the object itself. We only have to worry about how can we control its motion or trajectory so that both the human and object form some coherent interactions. So this whole on this box is from the object model itself. And as a result, we only need to worry about, or we only need to focus on the generation of the 6 DOF poles of the object. Another assumption we make here is the object is rigid. It has no deformation, right? So, this approach may not work, say, to generate a human, wearing a hat or wearing a jacket, something like that. Jacket may be highly deformed. So anyway, this is a very difficult problem. We made some initial attempt the input is a textual prompt. The person is gripping a large box at the front and the 3D model of the object. Right? Output is a sequence of a virtual human interacting with the object. So this is the problem setting. And we, starting from the generation model or diffusion model for human motion generation, right? So now we have two things to deal with. One is for human, the other is for object, right? And then naturally a simple baseline will be to have two dual branch model, right? One for human motion generation, the other for object motion generation, right? That's actually what we started with. And this is for human motion, right? So we start from Gaussian noise, and this is another diffusion model for object start from another, different Gaussian noise. And if we just do this separately, you can imagine, the generation of human and object will be independent of each other, right? So that's not a good idea. So, we can add some cross attention in between to allow the information exchange between two branches. So this approach is very simple and, it should be scalable, right? So, but the problem is which I'll show, let me show that to you and then I'll elaborate more. So this is what the output looks like, that simple baseline. Let me show play one more time. Right, so you can see the result actually is reasonably good because again, this is a very challenging problem. We got much worse result than this. So the problem is, even though the object can move along when the human rotates, but apparently the interaction is not good, right? Why? Because it violates the physical constraints, right? So for humans, if we like to hold up or grip a box, there should be some contact happening between the human body and object, right? That's the issue of this simple baseline. Right, in the generated output, there's no contact between human and object. And by the way, so for the simple baseline, it's scalable. We still believe in its potential, but for this particular task, there is not much data for us to play with, right? So as a result, we have to inject a lot of inductive bias to make it work. So in other words, if we could get more data, which unfortunately is a very challenging problem for human motion or human object interaction, right? You need very fancy capturing system. I know there's one here, but you can imagine still it's very time consuming, right? So probably that's the nature of this problem, right? So scaling is a promising direction, but how to make it really work is difficult. So like I said, we have to add some inductive bias to make it work, right? So I have talked about having a score function to basically tell us how good or how bad the model's output is with respect to some other constraints, right? In this case, we can also follow this fashion, and we can define a score function, a differentiable score function, to tell us how good or how bad in the model's output, the human and object, whether they form some coherent interactions. And then we can repeat this. And so what are some coherent 3D HOIs? So for the sake of time, I'll speed up and I'll skip some slides. I'm more happy to chat offline. Right, so first of all, like I said, there should be some contact between human body and object. And second, the object motion trajectory should be smooth, right? There shouldn't be some sudden rotation or translation of the object in 3D. And also, here is another trick, right? So in some cases, even though a human may, move a chair or something, but the human may also sit on top of the chair. The chair remains stable during the interaction. So we also consider, the static nature of the object during interaction to really encourage the 60-left pulse to not change much. So how can we do that, right? So really to define this score function, we need some affordance data, right? To tell us where the contact should happen. And on human body, which part should contact the box, right? Because you can imagine the contacting part will be different between gripping of the box or sitting on top of the box. So, and turns out this affordance estimation is a fundamentally challenging problem in both computer vision and robotics. Right? So what we did was to use a diffusion model, takes this texture prompt and 3D geometry of the object or point cloud, and it produces three types of output. First of all, contact points on object surface, contact points on the human body, and whether the object is static or not. So for the sake of time, I'll skip the rest and I'll go straight to the results. I'm happy to talk about the technical details. Right? So this is the result. So when we worked on it, no other models focused on the generation of human object interactions starting from textual prompts. So we had to make some modification of existing approaches. And none of them worked that well. So here's another one. A person holds a yoga mat. So you can see our approach can produce slightly better results than the rest, but still, there are some issues which I'll talk about later. And some user study, basically our approach shows better preference, and I'll skip this. Also, let me show you this actually. Right, so in the left are the estimated contacting points on the human body, and here are the final generation results of this person interacting with this box. Right? So it's reasonably good, but still there are some issues. So first of all, contacting area estimation or affordance estimation is fundamentally challenging. And here, another limitation is that we chose joints to represent human bodies. Right? Joints generally are good, but for this particular task of interacting with objects, we need to know more finer information about, like say on this. For my hand, which part of the finger have contact with the object, right? And also here, we assume that the contact or interaction is static, right? What if the dynamic interaction happens, for example, bouncing a ball, and then contact happens and no, yes, no, right? This is very difficult. And there are also concurrent work focusing on this, and we started looking at it. So check them out if you're interested in this task. Okay, so I was about to briefly talk about this our ECCV paper, which can generate stylized motion body. For the sake of time, I'll just skip it. And I have talked about how to generate 3D scene from a floor plan and then human motion. Code is available except for the first one, which will be released by the end of October. And so all this work were done with my excellent students and collaborators, some of them graduated from the Right, thank you.
So starting to go, please feel free, and if there's more questions, please come up and speak to the Professor Jiang. And pop quiz, which of these are brown grades?
When is
brown.
and